In this video, I'm going to introduce you to how Venn diagrams are used to model and solve counting problems. We're not going to go into full detail here. This is just going to be an introduction. We'll talk about more details on this topic later after we've worked some counting example problems. So, okay, with any counting problem, you're going to be able to identify what the system is. And when it comes to a Venn diagram, the system you draw as this rectangular box, okay? This is the system S. And what the system is so you take a step back and look at your counting problem from the biggest picture possible as kind of the most you can possibly have a complete overlook view of everything that can possibly happen in your counting problem. That's the system. So, for example, if the question is something like, how many different ways can you get a straight in poker? So you have a 5-card hand and you're dealing from, let's say, a 52-card deck. How many different ways can you get a straight? Okay, that's the question you're trying to answer. Well, what's the big picture in that scenario? What's the system in that scenario? Well, the system would be all of the possible 5-card poker hands. Not just straights. I mean, any poker hand you could possibly have. That would be the system. So this system here would contain all possible 5-card poker hands. And you want to think about that as you could list those out. You could make a list of, a big Word document with pictures. Here's one hand. So the order doesn't matter in a poker hand, but here's one hand. It shows all of the different cards, the 2 of diamonds, the jack of clubs, whatever. That's not a straight. You can't have a 2 of clubs and a jack of diamonds in a straight, but that's not what the system contains all possible hands. You could list all of those out. You wouldn't do that because I'm sure there's, millions of possible hands, but that's the hypothetical way you think about it. Okay, if you're thinking about how many different ways can a horse blackjack and another horse barbecue in a horse race finish first, second, or third, well, then the system in that case would be all possible finishes of any horse in the entire race. All possible first, second, and third place finishes. If you're rolling a pair of dice and you're trying to figure out how many different ways can you roll a 4, so like the final roll is the sum of the 2 dice numbers that come up, well, then the system in that case would be all possible outcomes of rolling 2 dice. So if you have a 1 and a 3, well, order doesn't matter here, so you're not going to, within the system, you're not going to have a 3 and a 1. You're just going to have all possible rolls. Okay, so that's what the system is of a counting problem. It's that you step back and look at the big picture of your problem as the biggest picture you can possibly look at it. I mean, we can't, when it comes to the poker hands, how can we get any more of a bigger picture than all of the possible 5-card poker hands, right? That's the biggest picture possible. And so that's what the system is. Now, within the system, as you're probably aware with Venn diagrams, you have these circles. They could be overlapping. They could not be overlapping. And these, like this is called set A, set B, set C. So what are these circles? Well, it's exactly what they look like. They're just these regions, these subset of elements within the system that you've chosen to put a window around. So if these are 5-card poker hands, set A could be enclosing all of the straights. Set B could be enclosing all of the full houses. Set C could be enclosing all of the hands that contain the 2 of diamonds. Okay, now, what you can think about, though, is that you want to draw these circles to where they're either overlapping or not overlapping, or the extent at which they're overlapping is correct. Because if I said this was all straights and set B was all flushes, well, you can have a straight flush. There are straights that are flushes and there are straights that aren't flushes. So in that case, set A and set B should be overlapping. So, okay, what you want to do is when you're drawing in sets like this, you want to make sure they're overlapping correctly. But the way you want to do this, though, is if you're not sure, even just a little bit, if the sets should be overlapping or the extent to which they should be overlapping, then what you want to do is just draw them fully overlapping to start with. So you would do, okay, let's say you knew for sure set A wasn't overlapping with any of these two sets, but you weren't 100% sure about set B, set C, and set D. So you just draw them fully overlapping and continue with the problem. And so what would happen is as you would go through the analysis, the mathematical analysis, which we'll talk about in a second how to do it, of the number of elements in these sets in these overlapping regions, if one of the regions isn't actually overlapping, you're going to figure that out. And so if the amount of elements in both B and D but not in C is 0, you're going to get that and you'll put 0 here, which is effectively saying that, look, there's no overlap between B and D. And maybe there's no overlap here, and then maybe there's 20 elements here. And then once you figure this out and you go through all the math, then you can erase this and draw it appropriately. So in this case, it would be, let's see, B and D and B and C don't overlap. Only D and C overlap. So you would do like this. What was it? B, I think it was C, D, like that. I might have mixed that up, but you get the idea. This one was 20. Okay, now you might be asking yourself, well, okay, this was all straights. Well, there's not that many straights in the system, so I should draw this circle smaller. Don't worry about anything like that with Venn diagrams. The size of the circles and the location of the circles and oh, look, I didn't draw this overlap large enough. All that doesn't matter. Okay, now, the next thing we want to talk about is that what A, B, C, and D, and S are, what exactly they are is these are sets. Like in mathematics, you have sets. That's what these are. Okay? So a set you can represent with a variable. Like you have, this is a set. A is a set, B is a set, C, D, S is a set. So, okay, it's going to be helpful if we understand some of the fundamental properties of sets. It's going to be really helpful to understand how we're using these sets to solve counting problems. Okay, so first of all, a set is a collection of elements. Okay, it could be any elements, not just numbers, any elements. It's just this list of elements. All right, now with counting problems, what the sets are more specifically for counting problems is the sets are collections of outcomes. Okay, the outcomes for set S, the outcomes are, again, I mentioned that you could make a Word document with a list of all possible poker hands, right? So that would be the elements in the set, S. All possible poker hands. Okay, now, and the elements in set A would be all possible poker hands that are straights. The elements in set B would be all possible poker hands that are, whatever I had said, straight flushes, but then these would be overlapping, but you get the idea. Again, A and B and S, all three of those are sets. These collection of elements. Okay. Within any set, this is like a rule for sets, there are no duplicates. This is really important to remember. There are no duplicates within any set. No duplicates. So when it comes to, since we know that order doesn't matter with poker hands, then any reorderings of the same set of cards aren't going to be in the set S. If order did matter, then they would be in the set S. So there are no duplicates within any set, no duplicates. Furthermore, order does not matter within any set. So it's not like I have set S, which is the set of all 5-card poker hands, but if I have another set, let's say I'm calling set P, and it has the same exact elements as set S, but they're just in a different order, then no, set P is equal to set S, that they're the same set. Okay, now, if you're wanting to indicate the number of elements in a certain set, which we're going to be wanting to do a lot when it comes to counting, we're really more interested in what is the number of elements in a certain set, right? That's the whole idea of counting. We're trying to find what the number of elements in this set is, the number of elements in this set is, etc. Then you indicate that you put this absolute value bar around the set, and that represents the cardinality of the set. So this you're saying the cardinality of A. So in this case, the cardinality of A would be M. The cardinality of B would be N. The cardinality of S would be the total number of possible 5-card poker hands coming from a 52-card deck, right? But if you don't have the cardinality symbol, you just have the set symbol, then that's indicating the set itself. Like you open the Word document and you see that list of all the poker hands. Okay, now what you can do is you have the ability to perform operations between sets, between 2 or more sets. Okay, there's different operations you can do, but 2 of the main ones are the union and the intersection operation. All right, so when it comes to union, what you're saying is that if I say I want to have this new set, M, that is the union of C and D, set C and set D, then what this new set contains is everything in set C and everything in set D, but with no duplicates, because a set can't have duplicates. And then, like, order doesn't matter. I could add, say, C union D union B. That would contain everything in set C, everything in set D, and everything in set B, but again, with no duplicates, and order doesn't matter. Same idea if I added a third set here, however many intersecting sets, I could add 8 intersecting sets, whatever. So set this new set P, which we say is C union D union E, would be everything in C, everything in D, and everything in E, all in one set, but no duplicates. All of this. If I added union B union A, then this set would contain all of this. Okay, now one thing to note is that when it comes to the union of sets, this union operation, and it's going to be the same thing with the intersection operation, order doesn't matter. So I could, this is equivalent to E union D union B union A union C. These 2 are equivalent. Order doesn't matter with the union operation. Okay, now when it comes to intersection, if I asked, okay, what is this new set M is C, and then with intersection, you do instead of like a U, you flip it, make the U upside down, that's intersection. So C intersection D, this set would contain everything that's in both C and D. So we can see the cardinality of this set would be 20. Okay, if we thought about a new set P that was C intersection D intersection E, this set would contain everything that's in C, D, and E. That would be here. All right, but then with just like with the union operation, order does not matter. So set P you could also write as D intersection E intersection C. That's fine. Okay, we can also think about the idea of subtracting sets, what subtracting sets means. So if I have some new set L that I'm saying is equal to, let me add 2 sets here. So F, G. So if L is equal to set F minus set G, what that means is that you're taking everything in set F and removing from set F any elements that are also common to G. So set L is this. You see, if I said set P is equal to set C minus set D, then I would be taking set C and removing this. So I would be left with set P would be all of this. If I also subtracted out set E, then the set P in that case would be all of this. You see? Okay. Now, we can also think about the idea of the opposite of a set, or like you can call it the not of a set. So I could say set P, this new set P, is the opposite of A, not A. You put this bar on top. What that means is it's everything in the entire system that's not in A. So that would be all of this. And again, for any of these operations, the reason why I keep indicating that we're getting a new set is because it is a new set, and it's also a reminder that there's no duplicates and order doesn't matter. Okay, so this is not A, all of this. We could say, let's see, we could say this new set M is, so you could do P, or not P, C union D union E not, so that would be all of this. Right? Everything that's not in C, D, and E. All right, now we can think about using this not idea, we can come up with a formula for the subtraction of sets. So set C minus set D, we could write as it being equal to C intersected with D not. Some new set P. So how does this work? Okay, so you're looking for everything that's in not D and in both C at the same time. So what's not D? Not D is all of this. Okay, now what's C? All of this. So what intersects both of those? Well, we can see it's this. Now I could add, let's see, if I added minus E, then I would add an intersection with E naught. And now in that case, this isn't intersecting with C anymore. Right? We're looking for the intersection. This isn't intersecting with C. This isn't intersecting with C, so we're left with this. Okay, now the next thing we want to think about is, so, okay, the system for any counting problem, you can think about how the system is sort of like an inherent property of that counting problem. It's like a material property. It's a fixed personality trait of that counting problem. Whereas these circular sets here that you draw, these subsets that are drawn within the system, are not an inherent trait of the counting problem. So what do I mean by that? What I mean is, let's say you had multiple people working that were given the same counting problem to solve. Okay, so they all start out, they're going to make a Venn diagram, they all draw the system. Well, for all of those people, the system is going to be the same. The system is the system, right? If we're counting a certain number of 5-card poker hands, well, the system's going to be all of the possible 5-card poker hands. It's like a fixed trait of that problem. However, when it comes to these circular subsets, what you could think about is the subsets that are added is completely arbitrary. It's decided by you, whoever's working the problem. I could draw a set here this is the all poker hands that contain a 2 of hearts and a pair of jacks, at least that. And then as long as they have those two features, then they're in the set, okay? I could draw another set that contains a face card and 2 diamonds. The hand has to contain a face card, at least one face card, at least 2 diamonds, then it's in this set, right? It's completely arbitrary. And so these different people that are working the counting problem could potentially have completely different sets that they've added into the system. There's like an infinite, well, I don't know about infinite, but like a huge number of possible subsets I can add into the system here. But there's only one system. You see the difference? Okay, and so now this raises a question then of, well, why do we choose to add certain subsets into a system for a counting problem? Why would we add this set here that's encircling all straights, or this set here that's encircling all flushes? Why do you choose to add certain subsets? Well, there's two main reasons. The first reason is that subset is either being explicitly mentioned in the problem question or is close to being explicitly mentioned. So by explicitly, I mean you might be being asked something related to straights in the question itself. So you're thinking, okay, let me draw a subset that's encircling all straights. Or what I mean closely related, you might not be explicitly being asked about straights. Maybe you're asked about straight flushes, but still straights are closely related to straight flushes. So you still want to draw in a circle related to straights. You see? And so, like, just to give an example, with a lot of questions, you're asked something like, what's the total number of ways you could get a straight, a flush, or a full house? Okay, and you think about this, and your initial reaction to a question like this is, okay, are these clearly disjoint sets to where I can just solve for the total number of straights, solve for the total number of flushes, and solve for the total number of full houses and just add those up? Or is it very clear that these sets are disjoint? Okay, well, if it's not clear, then you're going to say, okay, you're going to think about just draw a fully overlapping Venn diagram, and you know what you need to solve for. What you're trying to solve for is you're looking for, so if C is the straights, D is the flushes, E is the full houses, you're looking for the number of elements in C union D union E. You're looking for the cardinality of this. That's the answer you're looking for. Why is this the answer you're looking for? Because this new set is going to contain no duplicates. It's going to contain all of the possible flushes, all of the possible straights, and all the possible full houses with no duplicates. And so you get the number of elements in that set. That's exactly what you're looking for, right? That's a common problem, that you're just trying to get the union of a bunch of sets that you believe there's overlap to some degree between those sets. And so, but with the union, it's going to account for all those duplicates. It's going to take them all out. Okay. Now, the second main reason that you would choose to draw certain sets, certain subsets into the system is because, okay, let's just say we have a problem where there is no explicit mention of a certain subset of elements of the system, but you're still being asked to find some count that maybe it's not plainly obvious on how to just go and use the counting techniques to get the answer. Then the reason why from that point you would choose to add to do a Venn diagram analysis and choose to add certain subsets is because you know you're able to get those counts. Either you can request that information, you can look up that information, or you're able to actually calculate those counts. Right? Like if you've got someone working at a university and they're trying to get some information on the number of students, well, they have certain data they already have that at hand. The number of students that are freshmen, the number of students that are taking these classes, they have that information at hand. So they can say, okay, well, I can let me put that set in here, the number of students that are freshmen. I can get that information. It's already tabulated. I have this. I could easily count that. Then they've got all these sets that they have that set information. Then they can analyze and say, okay, is the number I'm looking for kind of contained within one of these intersecting regions? Okay, so that's the other main reason why you would choose to add certain subsets into the system. And so now the last thing we want to talk about is, well, okay, let's say we've got a bunch of sets or a bunch of subsets in the system with all kinds of overlap, etc. How do we mathematically get the union of sets, the intersections of sets, etc.? Right? How do we go about getting the number of elements in this set, for example? Or if there were like 6 intersecting sets, fully intersecting or whatnot, how do we get the numbers that we need? Okay, so here's how it works. Let's start simple. Okay, let's say we have just 2 intersecting sets. Now, keep in mind that the formulas we're about to go over are going to be inherently assuming that if it's 2 sets, 3 sets, however many sets, that they're all fully overlapping as possible. But that's fine because you can still start, even if you have 10 sets, you can start by assuming they're fully overlapping and use this formula to figure out, okay, look, here's the regions that aren't actually overlapping. You'll find that in the formula that, oh, look, this intersecting region is, the elements are 0. So then after you solve for everything, you can redraw the Venn diagram if you want with the correct degree of overlap. All right, so if this is set A and this is set B, okay, the formula is that's going to give us all the information we need about any unions, intersections, etc. It's going to allow us to solve for, so we have a value here that's, let's see, this value is all of the elements in all of A. This value is all of the number of elements in all of B. And then here would be like, A, B, not A times B, but let's just say this is C, I guess. This C is the number of elements in this intersecting region. So, okay, the formula is A union B, the number of elements in A union B. So that would be everything in A, the number of elements in all of A, all of B together, but no duplicates, okay, is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. That's the formula, right? And so you can think about how you'll in a lot of cases, you'll be able to get what A is. You'll be able to get what B is. It'll be tabulated for you. You can pull the information off the company website or whatever, right? That's the idea. That's one of the main reasons why you put certain sets or certain subsets into the diagram, because you can get those counts. And we can see why this works, because you have A plus B minus C. And because when you add all of A to all of B, you're adding C twice. And so this subtracts out one of the C's. Okay? But again, just note that for any counting problem, you could be technically needing to solve for any of these. You might have this information. You might have this information. And you're trying to get some, all what's in just A and just B. Or you might have this information, and you're trying to get that intersection. It just depends on the problem. Okay, now let's think about how this is going to work for 3 sets. So you have A, B, C. All right, and again, I want to point out you could start off this way with them fully overlapping, do the whole analysis, and you find, okay, this is 0 and these two are non-zero, and then redraw the Venn diagram to where you would redraw it. In that case, you would redraw it like this. Right, there's intersection of, so A, B, C, right? So there are elements that are in both C and B, but not A. There are elements that are in C and B and A, but there's no elements that are in just C and A. Okay, but let's come back here. All right, so the formula here goes like this. The number of elements in A union B union C is equal to, so you do the number of elements in A plus the number of elements in B plus the number of elements in C. Then you subtract the number of elements in, and now you go through all of the possible pairings where order doesn't matter. So that would mean that if order doesn't matter, we have 3 sets here, and we're choosing 2 at a time. So 3 choose 2. That's 3 factorial over 2 factorial. So there's going to be 3 here, 3 of these pairings. So, and that's going to be all the intersections. So we'll do A intersection B minus A intersection C, and then minus B intersection C. Okay, but we're not done yet. What we're going to do next is add now A intersection B intersection C. And there's your formula, which, again, depending on what you have, you can use this formula to solve for whatever you're looking for. Whatever's in this region or whatever's just in this region, whatever. Okay, and so now what we can think about is let's extend this formula to however many number of overlapping sets. If you had 10 overlapping sets, or at least you assumed they were fully overlapping to begin with, what's the formula? Okay, so it goes like this. If you've got the number of elements in, so A1 union A2 union A all the way to AN, okay, that's going to be equal to, so you're first going to take the sum from 1 to N. Let me do it like this. So I is equal to 1 to N of the cardinality of all of the AIs. So the number of elements in A1 plus the number of elements in A2 plus the number of elements in A3 plus the number of elements in A4 all the way to AN. Okay? Then you're going to subtract and then take the sum from, let's see, I might not be writing this technically mathematically correct, but the idea is this is going to be the AIs intersecting with AJs, where I and J go from 1 to N. And the number of these that you're going to be summing is just, you would do N choose 2, right? So A intersection, you're going to be, the sum would be A intersection 2 plus A intersection 3 plus A intersection 4 plus A intersection 5, all the way to A intersection N. Then you're going to do A2 intersection A3, A2 intersection A4. The total number of these, you sum all of those, but then you're going to have a subtraction sign out front. You're really going to be subtracting all that entire sum from this. Okay? Then from there you add. So this would be like I, J, K is equal to 1 to N, and you do A, I intersection A, J intersection A, K. And there's going to be, let's see, N choose 3 of these total. And you just keep alternating this pattern. So you'd subtract, and the sum, I, J, K, L is equal to 1 to N. A I intersection with a J intersection with a K intersection with a L. And then you would do plus the sum, and you just keep going all the way until you get to the, so here this is you have 4 of these, the intersection of 4 sets. Let's say N is 10, right? So you finally get to the last summation, but it's actually not going to be a summation. The one where we're doing the intersection of N sets is not going to be a summation. It's just going to be, so it's going to, whether or not it's a plus or a minus just depends on what it could be a plus or it could be a minus. Depends on what N is. So if N is 3, it's going to be a plus. If N is 4, it's going to be a minus, the last element. If N is 5, it's going to be a plus. And this is just going to be A1 intersection A2 intersection all the way to AN. Okay, and so there we go. That's the general formula you can use to analyze the interaction between intersecting sets in a Venn diagram. Now, again, as I mentioned at the beginning of the video, if you still feel a little bit confused, don't worry about it so much, because what we're going to do is we're going to go through, in the upcoming videos, there's going to be lecture videos talking about different counting techniques, and then there's going to be a series of like 7 long example problem videos, like a marathon of counting problems that you're going to work. And then after that, we're going to come back to Venn diagrams to try and make sure we have a full understanding of how they're used. We're going to come back to Venn diagrams again later. Okay, but before I close this video out, one thing I want to mention is, so you might look at this and say, well, okay, this is, with Venn diagrams, you'll see that we refer to, a lot of times we'll refer to this set A as, okay, this is a certain, the outcomes of a certain event. Set B is the outcomes of another event. Same with set C. And so we can think about, from the standpoint of events, the idea of, okay, are we thinking about like an OR criteria between these two events? So the number of outcomes that are A or B or C, right? The number of ways you can get a straight or a flush or a full house. Okay, or maybe we're thinking about this from the standpoint of an AND criteria, the number of ways we can get a straight and a flush and a full house. And so from that standpoint, if there's an OR criteria, then, we're trying to, it's like the sum rule. We're trying to sum the outcomes in A, B, and C. And that's what the union would be, right? But then the AND criteria would be like some sort of variant of the product rule. Do we, if there's M outcomes here, N here, P here, are we, multiplying M and N and P to some degree? Like, how does that work? Well, again, we're going to talk about this in more detail later. But what I want you to think about is this. In that respect, this is what I want you to think about. Okay, so if I did ask, what is the total number of ways I could get a straight, a full house, and a flush? What is the total number of ways I could get a straight, or a full house, or a flush? Well, then that would make sense to you want to get the union of A, the number of elements in the union of A, B, and C. That makes sense, right? We're just summing, because what are we doing here? We're summing all of these elements in these sets, but removing the duplicates. So that is exactly what we're doing. All right, but now when it comes to the AND criteria, okay, if I'm then asking something like, what is the total number of ways of hands that I have a straight and a full house and a flush? Okay, well, what am I talking about there? If you think about that question, what's the answer to that question going to potentially correspond to? Are we going to need to be multiplying these outcomes in some way? And like just all of A, all of B, and all of C? Well, no. What's the number of elements in this region? What is this region here? Any hand in this region is going to be a straight, a full house, and a flush, which I don't even think is possible, actually. You can't have a full house. If you have a full house, you're not going to have a straight, I don't believe. But you get the idea, right? In this region, the answer to that question would be 0 then. But let's say that there was an intersection for all three. Here's we're looking for the number of elements in this region, you see? It's hands that are all three of those criteria at the same time. So what that should suggest to you is that with Venn diagrams, with correctly laid out Venn diagrams, you can answer both or. You can answer either or and criteria with this formula here.